All right, so ladies and gentlemen, we'll continue with the program. We're going to listen to a presentation from the CEO of Mivium. Mivium is a GaN company, which I think you'll find very interesting. Speaking on behalf of Mivium is Eric Tsai, who is the co-founder and CEO of Mivium, where he leads the overall strategic vision and oversees the entire business. Eric is experienced in building global brands while operating global supply chains. He previously pioneered numerous hyper-growth business innovation for multiple startups to Fortune 100 companies. More recently, he served as the Vice President of Marketing and Business Development for Joybird, a direct-to-consumer brand he helped build from $10 million to $200 million in revenue and was later acquired by Lazy Boy Corporation. During his tenure with Joybird, he amassed $790 million in total revenue for the business. Eric's work has been featured by Google, Meta, Pinterest, as well as in publications such as VentureBeat, Forbes, CMO.com, Entrepreneur, and Internet Retailing. So, Eric, great to have you with us. We're looking forward to learning about Mivium. I see you have the presentation loaded up and you can control it, so I'll turn it over to you.
All right. Thank you, David. I appreciate that intro, and welcome everyone. My name is Eric. Like David said, I'm the CEO and co-founder of Mivium. Kind of continuing on for Tori's presentation, I think he had a good point about power being the problem. I think you're going to find a lot of solutions that Mivium is going to be providing that's going to be very interesting for you guys. So let's first talk about kind of what the problems that we're solving here. Our mission is to solve the world's toughest semiconductor challenges, right? It's including most of the problems that Tori actually discussed. And by doing that, we're going to accelerate the world transition to gallium nitride, which is the new material that everybody is talking about right now. And we're going to go into a little bit more detail as to what that really means and why this is going to solve those problems. First, I think we need to understand that why we need AI, why we have all these technology advancements. Look at it. Every 2 years, more data was created than all of humankind history. Like the last 2 years, we created more data than what humankind in history did, forever. So imagine the amount of social media data, the amount of sensor data on your phone, right? The amount of data center data that needs to be going back and forth. It's not just storage, it's not just transmitting. There's a lot more data creation aspects of it as well. So with all that data, you need processing. However, the challenge that we're seeing today is that data growth is outpacing our ability to process it. Right. So if you look at compute, which is what, again, Tori talked about, compute, why NVIDIA is blowing up, is doing really well, is because we're shifting from CPUs, right, which is kind of having issues keeping up, as you can see from the slide, that putting more transistors doesn't give us more performance. And so you see the chart right there, the clock speed remains kind of flat now, ever in the early 2000s, it's starting to early 2000s into like 2020, because by shrinking transistors, putting more, we're actually not seeing improvements. And so what does that mean? Well, that means that we need a new CPU, right? The new CPU is actually the GPU. It's fueled by this NVIDIA AI boom that everybody is seeing right now. And so if you can look at the chart that's on the graph right now, right here, you see the 40 years of microprocessor that it kind of just plateau out in the early 2000s, like I showed you in the last chart. However, because of the proliferation of AI, GPUs now becoming the new CPU is giving us that new trajectory, that line that's coming up again, right? And so the thing about GPUs, right, is that GPUs are all residing mostly now in data centers. Of course, as I say that, Jensen just announced that they're going to have a $3,000 personal computer with super GPUs in it, right? But that before that, it's really reserved for data centers. And so you see what I think Tori talked about, the network is the computer. What he meant is that the whole entire data center is your computer now, and you need the internet connectivity to connect to it. Then the data center does the processing for you, right? So the new unit of computing powering the AI is actually the data center. It's not the laptop and the phone that you have on your hand. Yes, they're still powerful, but if you look at the last 3 to 5 generations of iPhones, they're not that much better and faster. I mean, if you switch it every 2 years, you will barely know huge differences compared to the first few generations of phones that you receive. And so that's because we're hitting the limitations on materials within those phones. It's specifically about semiconductors. But again, AI is the key driver right now. And you can see the demand for data centers because of the AI workload that's needed. And you can see also on the chart right here, you see the workload for non-AI is kind of plateau out, right? It's kind of growing at a 16% CAGR, whereas the AI stuff is going nearly 40% CAGR, right? So those demands is because we Americans love AI and we need data centers. And you can just see these two charts that the US has more data center than all other major countries combined. I mean, we're talking about 5,000 plus data centers, and the next in line, Germany has 500 data centers. UK has 500 data centers. And not just that, right? More data centers are on the way, right? This year, there's going to be 4,750 data centers being constructed, and we're just keep going, right? So again, this is why the power is going to be an issue. And as you can see, AI boom threatens data center power efficiency. When we talk about power efficiency, it's because there are non-AI data centers related equipment and needs. But once AI comes in, it just sucks up so much power, it creates a kind of imbalance of the powers that needed for the data centers to run. And so not just that, right? The major problem with data centers issues in terms of power outage is the power and cooling are 71% of data center outages. You think about it, right? If your internet is down, if somebody's work, computer is down, if you can't access the AI that's helping you at your factory, that's going to reduce productivity, right? It's not just the dollar that you pay, for the companies that you're giving you the service, but it's actually productivity. And so if you look at it, that is why power is an issue, right? And power and cooling is an issue together, because when you run high intensity AIs and GPUs, they get super hot. And when they get super hot, they need time to cool down. And I'm not sure if you guys all realize that Blackwell, NVIDIA Blackwell was supposed to ship last year, end of last year. They had to delay it because they had some issues with cooling. And now you're also seeing companies now with liquid cooling technology coming in, right? Liquid cooling is not new. I mean, it's been around for 20, 30 years now. But now they're using it massively to implement into data centers. And there are many startups and mid-tier companies start implementing these liquid cooling technology. All in all, when you implement additional things like this to a data center, what is it going to do? It's going to increase your costs, right? It's going to significantly increase the cost of running a data center, running those servers, and then you're pulling in more power. So not just that, right? Kind of closing off on the power demand. Besides data center needs, we're also using a lot of our phones, our mobile devices, and also the internet, right? So you can see the energy forecast is tremendous. It's almost like going 45 degrees up in the next 5 years, 10 years. So what is the challenge that we're facing, and how are we going to solve this? Well, computer chips like CPUs and GPUs are silicon-based microprocessors. And so we're reaching really the silicon's limit, silicon's physical limit. So the next thing that we believe that we can do is to introduce the new silicon, right? The new silicon is a Nobel Prize winner super material that's shrinking phone chargers, fast charging EVs, unlocking the most advanced defense systems, and making 5G, 6G possible. Is GaN, gallium nitride. Now you can say, well, I've heard of it, I've seen it. Tori just talked about GaN. Yes, there are GaN out there. In fact, GaN is a material. It's better, faster, more reliable than silicon every way. Right? Here's a little bit of technical way of looking at it. But to make it simple to look at compared to silicon, GaN essentially can make any power devices smaller in form factor because it reduces other components that's needed because the way how efficient it is, and also that it essentially does more by being smaller and less, right? And it also has a faster switching, meaning that when you turn on and off, you don't lose power during those efforts. And then in terms of the material itself, it has also a very good thermal conductivity, because that means that it won't get as hot as silicon, right? So some of the problem that silicon-based microprocessor faces is that it actually melts, right? And it gets so hot during those processings. So GaN wouldn't have those issues because of the way that the property of its material. So why aren't we already using GaN? You may say, well, if it's that magical. Well, the thing about GaN is that it is, right? It is starting to, the market demand is actually skyrocketing across multiple industries. You're talking about, again, the most popular industries are the defense industry, the communication industry, and aerospace, right? And also now is coming in, in terms of Tesla, they're actually start producing and testing, putting GaN into their cars right now, in terms of, the news that you see on the top left. The SK, the foundries in Korea are starting to put in GaN power semiconductor into Tesla, right? What the simple way you can look at GaN is that if you go to Amazon and you start searching for GaN chargers, you're going to find these GaN super fast chargers that's going to charge your phones, 100 times faster to 200 times faster than any other charging devices from your default, manufacturer, right? It's because they have a little bit of GaN material in there that's making it that much better, right? And so in terms of that material, it's so great what it can do. So why isn't GaN, being produced at scale and commercializing it? Well, the answer is this: it has many challenges, right? So for one, it is extremely complex and toxic and costly to manufacture. It costs a lot of money to make, and it's very complex material to produce. And right now, what they're doing is they're producing GaN on top of silicon. They put a thin layer of silicon and then they grow GaN on top of it. They call it GaN on silicon. So 90% of the GaN is grown on silicon. Well, silicon is already an inferior technology. So when you're doing that, you cannot grow a thick layer of GaN on, and also it's very expensive to do that, and it's slow. So it drives the cost up. And so on top of that, you can't produce a high quality version of it without defects, right? So it's expensive, it's complicated, it gives you defects. That means that for every 10 you produce, maybe you can use 3 of them, right? Again, that drives the cost up, which then limits your scale, right? Limits the ability to make bigger wafers to produce a lot of them. So that's the challenge that current GaN is facing right now today. However, it doesn't mean that people are not producing them. I mean, the GaN that you're seeing, the fast charger, are the very low grade ones, right? That is not really super semiconductor grade that you're going to be using for aerospace. Aerospace, they have the high quality GaN, but those are extremely expensive, very slow to produce. And so this is where Mivium comes in, right? We actually have a patent process that's able to manufacture GaN in volume. We're talking about, somebody that can produce a high quality GaN for Raytheon. They can probably make 1 wafer in 3 months. And we can probably make a wafer, 100 wafer every hour, right? Once we start to scale. And so the difference between that and us is that right now, the current semiconductor manufacturing methods for GaN, it's inconsistent, it's very toxic, like I explained to everyone already here before, and it limits your production capability. Our process is completely different. We use a physical process that creates a chemical reaction without catalysts or other contaminants. That means we don't have toxic stuff coming out or going in. We reduce that process, reduce time, reduce the cost. There's no EPA coming after us. And in terms of our manufacturing costs, and our automation process, it also reduces that significantly. In fact, we believe that we can produce our GaN at the same cost as silicon as time go on to match that, so that we can actually take over the market share. If you have a choice to buy material that's the same price as silicon, but that's so much better, wouldn't you switch, right? So that's kind of like our approach in terms of go to market. And then we also have our patents on it, for our methods and equipments and everything. So this is kind of like a slide showing you the difference between us, right, in terms of our manufacturability, our reliability, and our IPs and everything. So overall, our process is also much more reliable, and our product is going to be proliferated in many other devices. And the way to look at it is this: semiconductor materials, right? It's the most upstream, meaning that everybody have to get material from somewhere. I mean, the guy above us are the mining people. We're talking about the Rio Tinto of the world, right? They're the guys that go and mine the actual, bauxite ore, and then, process them and purify them into gallium. And then we take their gallium and then we process with our patent technology into the gallium nitride that we're going to be delivering. So kind of share with you guys what our patent process does. It actually unlocks the true potential of GaN. You see GaN is already delivering high performance. It's doing great things. There's a company called Navitas. You can go to their website, you can find a lot of their presentations. They're using existing GaN technology to produce whatever they're doing right now, and they can show you how efficient it is. And so here's a way to look at it, right? Existing semiconductor materials, you can see the products within these circles right here, infinity circles, right? So you can see these products that uses GaN, product that uses silicon carbide, and the product that uses silicon. So on this chart, it's very kind of easy for everyone to kind of see, okay, right now, like what Tori said, GaN and silicon carbide is going to be outgrowing potential, right? That's what he talked about. Well, here's the reason why: because most of these products are using these materials right now. However, with our technology, we're able to expand the GaN's platform's kind of capability to massively even higher operating frequency. So when we're expanding the true potential of that material, what's going to happen to those products that you see on the screen? Well, the products are also going to go perform much better, much higher, much more efficient, because the property of the material is fully realized. So hopefully, you guys can see that our GaN can really not just bring a scale to it, but also improve the existing products out there. And I often tell investors that it's really about thinking about putting a 200 octane gasoline into your car. You don't have to change anything about your car, but your car is going to go much faster because of the gasoline that you put in, right? And gasoline is like the material that you put in to start burning the fuels for your energy for your car. And so looking at the kind of addressable market, existing GaN substrate market size, it's about $5 billion right now, and it's going to be about $13 billion by 2033. And again, this is the existing GaN market, right? Meaning that the expensive, the not scalable, right, the not reliable GaN compared to ours. So we believe that our market is much, much bigger than this. And this is why we're investing a lot of efforts and time into doing this right now. And so here, with the next slide, I want to share with you guys the product roadmap here. Right now, you can ask us, so what are we doing right now? How do we bring this to the market? Well, we have a phase one, which we're going to produce GaN particles. Particles are like powders, right? They're kind of like the flour to make the bread, right? So essentially, we're making these GaN flours, GaN particles, right? And the first step is to make a prototype of it, and then take the data from the prototype, and then we're going to create then pre-production pilot. Say, okay, we can make from a bag of it to make buckets of it, and then eventually, when we go to the commercial production, we're going to make truckloads of it, right? We've got to do it in steps, because this product, the way that it is right now, has never been produced this way before. And so it's important that we learn as we go, and then as you scale, we have to also be mindful about how that's going to change the property of the material, and also being able to kind of build a facility around the scalability of our technology. So once we're achieving the GaN particle powders, right? Then the powders, we can take our own powder, take the flours that we produce, and then we're going to essentially make bread out of it, right? And then the bread, or the pizza out of it, right? So pizza is a round shaped thing, just like the substrate wafer that you see right there. So we can then sell both the powder and the wafers, right? And then we're going to start with the 4-inch, and then we're going to gradually go into 6-inch. So you can tell us, why do you need to sell the substrates? Why can't you just sell the particles? We can. Yeah, we can do whatever we want. But again, since we're the most upstream, somebody who's going to buy our particles, our powders, they're also going to turn the powders into substrates for their usage anyway. So we can actually take ownership, control of the market, should we want to do that, right? So again, here's the kind of like the roadmap to show everyone where we're going with this. And now that kind of like the two products that we're looking to develop right now, we're talking about our business model here, where we take the gallium, we process them into our GaN particles, and then we can sell to companies like IP companies, right? You're talking about semiconductor design companies, fabless companies, right? Foundries, and electronic design automation companies. Those companies are at the design front of things, like ARM, ARM. I'm sure everyone heard about ARM, ARM, Apple, NVIDIA. They have designers. They don't say we want GaN. They get a marching order from their CEO or their VP of products and say, hey, we need the next iPhone to be performing at this level. We need the next GPU to perform at this level. What kind of spec, what kind of material can you get to meet these specs? And that's where we come in to play, to be able to sell them these particles so that they can go and develop the products they need. And then these companies obviously can take our powders, right, integrate it into their production and their design, and then start producing, these 5 categories of products that really we're targeting, which is power electronics, photonics, aerospace, telecommunication, and biotech and life science. Now, that's the first revenue stream, is selling powders, selling the flours by itself. Then once we are able to produce substrates, right, these wafers, there are companies that just want to buy wafers. right? Because they already have a process, they have equipment, they have people, they know how to take a wafer and turn it into products. So we sell these substrates to integrated device manufacturers or IDMs, right? So these are companies like the Samsung of the world, right? Texas Instruments, because they have products that can just swap out, whatever material it is from the wafer, and then being able to produce a product that performs much, much better, right? So kind of going back to my 200 octane gasoline example, it's kind of for these type of companies. So overall, we can kind of, take ownership of the market from the beginning by selling the powder first, and then being able to say, farther downstream to sell the substrate. So these are the two options that we're looking at right now for our business model. And then last but not least, I want to kind of share our team business timeline to kind of give everyone where we're at right now. David already kind of shared with you guys my background. I've exited a few companies, and I'm an entrepreneur, and I'm a problem solver. That's really who I am, right? But the exciting thing for me is the team, right? The team that we have 2 PhDs who used to be applied material executives, and they've been in the industry for 30 and 40 years. And also we have all 3 of them, the Gino, Chandra, and Jim. They used to all work together and apply material at some point, right? And then we also have Rick. He's the son of the Jim, who is the inventor. He's the patent holder. And then we have a securities counsel who's helping us, with our capital raise, securities laws, and everything. So, in terms of our capabilities and our team, right, especially Chandra, he used to be a professor at UCLA teaching material science. He exited, multiple startups, even including a $100 million deal to, I think it was Intel. And then, Gino also used to work in Novalis, who was later on acquired by Lam Research. So these guys have been around the block. They know what it takes to develop products and develop equipment. So at the junction of where we are right now, kind of wanted to share that, we actually started this concept. Jim, right? He's the patent holder. He started thinking about this in 2012. And it took him a couple of years, right, to take that concept into a patent, and then being able to develop his first concept where he did that kind of in China. And then he came back and decided to, have his son join him and started a company in America. And then that's when they brought me on, and then kind of strategize how we're going to raise capital and how we're going to, kind of tell the story of how we're going to deliver and bring this magic material, to the world type of thing. And so now we're at the stage where, a year ago we raised $1.3 million, and we're still raising money right now. And we onboarded these 2, executives, COO and CTO, just last year. And then we're actually focusing on producing our first GaN particle samples right now, and we're hoping to do the commercial pilot next year. So I want to share kind of the last thing is kind of our traction and go forward strategy. Our milestones is to commercialize production in 3 years. So in 3 years' time, we hope to start, building having the factory producing commercial volume of the GaN particles. And up to today, we have raised $5 million through our equity crowdfunding. Our current company valuation is $22.6 million, and we're actually still accepting investments with only $500 minimum, right? And we got those $5 million from 1,200 plus investors. And, as I explained to you on our team's experience, we have over 100 years of combined expertise in semiconductors, right? And there's also 11 plus patents, including international methods and equipment. And we're committed to build our facility in the US. We actually applied for CHIPS Act funding, and they actually instructed us that, they would love to fund us, but they don't fund startups. So we're kind of instructed to kind of apply for SBIR grants and stuff like that, which we're doing right now. And also, our CTO, Chandra, he used to work at the National Science Foundation. He was a member, and he also advises the government on CHIPS Act previously as well. So, we feel confident that we're going to be able to get funding, non-dilutive funding, in addition to, kind of equity financing as well. So this is where we are right now. And, going back to, the phase where we are right now in terms of the phases, we're actually at alpha, which is the GaN particle prototyping right now. And we're confident that we're going to have the prototype alpha GaN particles in hand probably in Q3 of this year. So once that happens, then we're likely to raise another round of capital. And this is where we stand. So just want to share with everybody that this is the traction that we're getting right now. And if you're interested in investing and find out more about the company, all of our bios, all of our documents are at equifund.com, which is where raising the capital, the portal that's raising capital. And that's it.
All right, Eric, thank you very much. That was a very nice presentation. It was very disciplined and very methodical. I like the way that you started off with the big picture about all the demand drivers for GaN, what the current problems are with other companies that are trying to produce GaN, and how you may have a solution to satisfy that demand, and the solution can do things that other companies haven't been able to do. And talked about your roadmap and management team. It was very well organized presentation. So if you have questions for Eric, you can raise your hand icon, or you can type in a chat. But a couple questions. Can you talk about the capital intensity of producing those powders?
Yeah, so because of our patent technology, it is actually significantly lower, right, to produce our powders than any other technology out there, because we're using a technique called mechanochemistry. You can Google it, you can look it up. Essentially, right now, 100% of semiconductor materials are carved out of chemistry, right? But this is physics, right? This is very different than chemistry. And that's why I shared the timeline. Since 2012, the inventor was looking for other people who may have thought the same thing, but he couldn't find anybody. He just couldn't believe that nobody is thinking this way. And so finally, he decided to do it himself. And again, all three executives that we have, they're all 70 years old, and they've been around for 30 to 40 years in the industry. So in terms of cost, they know that it's expensive. And for us, it's not that expensive to produce them. And then we believe that with the next round of financing, we should be able to build a proof of concept commercialized pilot that shows that, hey, we can produce buckets of it, right, which is will be enough to kind of show people that, hey, we need probably $30 to $40 million to build a facility, as opposed to $200 million, right? Think about the typical fab that you need is way more than that.
So when you start selling these powders, will your customers turn these powders into wafers?
They can turn the powders into wafers, or they can get somebody else to turn them into wafers. They can also use them directly to grow other materials. Does that make sense to you? Because then, so if ARM or Qualcomm decides to build a chip for certain usage, they can say, hey, I want you to add this powder in there. It'll give us these functionalities.
Uh-huh. And so I believe in previous discussions you and I've had, correct me if I'm wrong, but the company, whoever it is that turns the powders into wafers, can use the existing equipment. So even if they're a silicon company or silicon carbide company, whatever, they can use some of the same equipment they have to turn your powders into wafers. They don't have to buy all new equipment. Is that?
They do not. They do not.
Okay. That's a big deal.
That is a big deal. And then the other thing I want to point out, that GaN isn't only a high efficiency technology, it also is a lateral technology. It means that circuit elements can be integrated monolithically into miniaturization and adoption of other approaches, like concerning device protection, ease of use, and reliability. So you're thinking about, for example, you can use GaN to build solar panels that powers your car, and your car powers your house. Because the way that the technology work together, and you're not losing anything going from one device to another. And that's the problem that we're seeing right now, right? Same thing with data centers, AC to DC, DC to DC. There are these challenges. They don't have to go to nuclear power if they use GaN. And we believe that strongly. And there's other people, experts in the field, that believe that as well.
So I believe you said that generally speaking, GaN throws off contaminants and noxious fumes, bad things like that. But your process avoids that. Is that
yes,
right?
Yes, because the existing process, they have to use materials in there that they need to take out later. And if they do that, they usually use like hydrochloric acid, right? 99% bleach, basically, right? The one that you have at home is like less 0.1%. They're using 99% to take stuff out, right? And when you take stuff like that, using chemicals like that, you need cleaning, you need a lot of multiple processes to wash and clean. That's why if you watch videos of fabs that does that, there's all these robots going back and forth. TSMC has them as well, right? They have to constantly, go through those mechanical processes to clean those out. It costs a lot of money. And then you have to, take it and take care of the toxic waste as well, right? That's another thing about EPAs. That's what we talked about as well.
Okay. And can you tell us about any large companies or the Department of Defense or Department of Energy, any very large entities that are very serious about GaN and investing a lot of money or speaking about investing a lot of money in GaN?
Yeah, I mean, there's a company called GaN Systems, who was acquired by, I think, Global Foundry for 850 million, just like a year or so ago. Because they're essentially acquiring all their patents. I think there's some 40 plus patents. The challenge that with GaN is that everybody knows, like we didn't invent GaN. Everybody knows it's magic, it's cool, but nobody can actually produce it the way we're going to be producing it, right? But the workaround that people have are all those patents, the workarounds. Does that make sense? And so the government knows that too. In fact, we're applying for a lot of DOE and DOD grants right now, and they specify these type of things. They say, can you, find something that that's GaN related, but without toxic, right? There's things like that. Or can you make solar panel more efficient? I mean, there's so many that just came out recently because we have a consultancy that we work with, and they're telling us like they're blown away because they've never seen that many before, right? And obviously, we heard in the news that China just banned, gallium, export to U.S. So that kind of, I think, even made the government more urgently, looking into this more aggressively right now.
Is there gallium in Greenland?
Here's the thing about gallium is that you can refine it from bauxite ore, right, which is what aluminum. And if you look up who owns the aluminum market, is China, right? And so that's why they own most of the market. But companies like Rio Tinto, they own a lot of aluminum ores as well, and we can get gallium for Australia, and Canada is also starting to do that. And there's many American companies now they're starting to looking into purifying gallium as well. And those are pretty big deals right now. There's also a big, I think, like mine that's been discovered in Montana recently that is said to have 100 billion plus gallium, in there. So it's all coming through, but it's just nobody can figure out how to process them. Just keep that in mind. I think 50 years ago, when people found gallium, they just throw them away through the process. When they're refining aluminum, they can get some gallium. They actually have no use, and they throw it away. Now, it's a completely different story.
Okay, so maybe the last question again. Your secret sauce is something like taking processed gallium, pulverizing it maybe, and modifying it so the powder is valuable to customers.
Yeah. So to make it, I don't want to go too technical, right? But when you make something really, really, really small, like sub 1 micron, okay, I think right now the technology enables companies to make gallium powders to 4 to 5 microns. But we're going to go below 1 micron, right? I think in a half a micron or below, right? And so when it's that small, you can atomically build a GaN structure, like a GaN molecule structure that's perfect. And that's what we're doing. We're essentially making, instead of companies growing GaN on top of silicon, we're growing a thick GaN, one piece, right? And that whole thing has great quality and performance and purity. And then they can put that on chips, put that on anything they want, and it's going to have the property of what GaN should be doing.
Okay, great. We're a little bit over time, but that's fine. Eric Tsai from Mivium, thank you very much for introducing us to Mivium. Very interesting story. We appreciate your time. And so we can end the presentation here.
Thank you.
And yeah, that was great. Great. So yeah, that is our program for today. Hope you learned something about the semiconductor industry and GaN.